Okay, so last question, the last question for me is motion, question 4. And I'm not sure that that title is going to give me any clues. Ball X is released from a height h and hits the ground with speed v meters per second. At precisely the same time as ball X is dropped, ball Y is launched straight up from the ground at v meters per second. Show that the two balls pass each other at a point quarter of h from the release point of ball X. Right, I think the diagram might be a good way of starting this one. Okay, so we've got, here's our height, let's call it y going up there, here's our ground. So ball X is released from a height h. And then that goes into free fall, hits the ground with speed v. That's ball X still, but it's sort of hitting the ground with speed v. Kind of straight away I'm thinking potential energy being converted into kinetic energy. So mgh equals half mv squared. Actually, I'll write that down straight away, because if we take our zero potential energy here, then you've got mgh potential energy, you've got zero kinetic energy because it's rest. Now you've got zero potential energy, so it's all kinetic energy for half mv squared. So we cross out those, and straight away we can see that v is related to h. So if I know h, I know v. If I know v, I know h. Okay. At the same time, ball y is launched straight up from the ground. That's y at speed v, and it's going to get to exactly the same height as that one, because this is sort of the exact opposite. This is half mv squared and no kinetic energy, sorry, no potential energy, so when it comes to rest, just before it moves back down again, it's got to have mgh potential. Instead of half mv squared, it's going to be the same height, which is probably going to be quite useful. So this is going to go up and down again. And this one just comes down. And the question says, when they pass each other, it happens at a quarter h from the release point of x. So if we go down a quarter, so it's saying that when ball X is there, ball Y has got there on its way up. Makes sense that it's got to be nearer the top than the bottom, because this thing's moving faster than that one to start with. So it's going to be above halfway somewhere. Okay, and we want to show that that distance is h over 4. Okay, so I'd just look at kinematics, I think, to start with. If we work out how x moves, how y moves, and set the positions equal, hopefully that will give us some clues. It's not entirely obvious at this point, but I would say, how does x move? Well, I'm going to be interested in positions and velocities and things. So I would draw from kinematics expression. So our distance moved is our initial velocity times our time plus half times acceleration times time squared. So that's distance moved. Initial velocity, t is time, is acceleration. And we're going to need this for ball X and ball Y. And so I think we're going to have to be a little bit careful about positive signs and negative signs here, because these are moving in opposite directions. So I shall define that as 0, and my distance, let's call it Y. I've already done it there. So distance there going up like that, which means that my acceleration is going to be minus g, and distance moved ball X is going to be negative. So let's just watch that. So let's do ball X. So initial velocity is 0, so u is 0, acceleration is minus g, so my distance moved is going to be minus half gt squared. That's that distance from there to there. If I want to write that in terms of y, that'll be height minus y. No, that's the other way around, isn't it? It's y minus height. Where it is now, minus where it was to start with, is a distance moved equals minus half gt squared. So y for ball X is h minus half gt squared.
Just a point, is that going to be a little bit confusing, having h as the height that X is at that point?
No, height isn't, no. Height is where it's released from.
So y is that point there?
Y is that point there, y of X. And therefore,
that's right, because it's negative.
Y minus h is the distance moved. Yeah. So yeah, that's all worth thinking about. Know what symbols are being used for what here, because there's a lot of them. Okay, so as we can see, t increases, or t equals 0, it's going to start at h. As t increases, this thing is going to go down. So that seems sensible. So ball y, initial velocity is v, which is going to relate to there, but let's just leave it as v as the moment. Your distance moved is going to be the height, y of x, because it's going up from the ground. Again, acceleration is minus g. So we've got s, which is y, so y of y, equals initial velocity times time, plus half times acceleration times time squared. So that's the other one. Now we're saying the balls are passing each other. I'm working the wrong way across the whiteboard. So obviously yx equals y of y, and they pass each other. So h take half gt squared equals vt take half gt squared. These two terms are the same. Let's get rid of those. So h equals vt. Does that tell us anything useful? Yes, it does, because it tells us that our time, because we know h, well, we assume we're given h, we know v, which is going to be related to h. So therefore that tells us what the time is when they pass. Therefore we can substitute that into that one, or equally should go into that one, they should give the same result. And that will tell us our distance. So substitute to y of x, or equally it should be the same if we go with y of y. So y of x is h minus half gt squared, so that comes to h squared over v squared. V squared is related to the height by our energy, so energy says that we want v squared, so v squared equals 2gh. So y of x is h minus half g h squared over 2gh. It's goodbye to the g's. Here we get 2 times 2 is 4, and we lose one of the h's, so that's h minus h over 4 3/4 h. So that's that distance there. So this distance is 1/4 h. So distance travelled, just that last bit, equals h minus 3/4 h. 1/4 h. That's quite involved.
That's good.
There might be a quicker way of doing that, but
I think one of the misconceptions could be that people might assume that the velocity is the same when they're passing each other. There's something seems like it would want to suggest that, but it's not the case.
yeah,
And that could throw people and lead them down a side track. Or would they?
yes, because this is going to have
Well,
a
they
large
will.
lost.
No, maybe they would
velocities are
actually.
the same.
Maybe we can use that then. Is it?
Velocities are going to be, because these are symmetrical
Yeah, they're pathways.
things. If they're the same height, same potential energy, they've got to have the same kinetic
Oh, they're
energy.
thinking it. Yeah.
So they're equally.
Does that help in any way then?
I don't
I just
know.
wonder.
Does it help? I think that's just another way of rephrasing.
Yeah.
You might be able to use that one. No, but that's just a rephrasing of
Not
energy.
the same thing anyway.
Because
Yeah.
you've got v squared minus u squared is 2as half mv squared minus half mu squared equals ma times distance. So it's the same. Changing kinetic energy is potential energy. So that one is just a statement of energy.
Yeah, it's not going to happen.
That's not going to help.
I think your solution has the same, it resonates with other scholarship questions we've seen and the amount of
Yeah.
maths to...
There is some, this is kind of algebra really, and I think there's a lot of traps in there. Watch those negative signs. This one is going downwards, this one's going upwards, so you know whether you have a positive distance or a negative distance. Yeah. It's
That's a good one.
quite nasty. And they only give you 1, 2, 3, 4, 5 lines to do that in. How many lines will I take to do that?